Hello, so today you are looking at fast exponentiation, or sometimes also called exponentiation by squaring. And so this basically is when we want to compute x to the power of n, it's where this applies. So let's say when you usually compute, let's say x to the power of 2, you do x by x. To compute x to the power of 3, the usual method is this. X to the power, let's say, of 6, we do it 6 times, right? And so you get the idea that this becomes really too much when the exponent is really big, right? And so, but essentially you can see repetitions here. Basically multiplying these two is getting x squared is the same thing as multiplying these two, the same thing as multiplying these two, right? Or also you can look at it as multiplying these three x's is the same as multiplying these three x's, right? So there is potentially a way to optimize this, right? And so this is what exponentiation by squaring, the term usually is called exponentiation by squaring, refers to. So basically, essentially, it's just when for large integer powers, it's really useful to split the exponentiation in a clever way into a series of squaring operations and then multiply the result of those. And so to just put this in a kind of a formula, what this looks like is that x to the power of n is equal to x to the power x squared to the power of n divided by 2, right? This essentially, if you look at it, this is just, well, x to the power to this is just x squared multiplied by this. That's just how powers work, and this is just this. So that's trivial, right? But this would work mostly if n is even, because if n is odd, then 3 divided by 2 is 1.5, right? And it doesn't make sense to make this exponent. And so to avoid this, what we can do is just make it really simple. Just convert n, so if n is odd, that means that n minus 1 is even, right? And so this formula can apply if n is odd, if n is even, right? So this part of the formula can apply if n is even. And if n is odd, what we can do is just do the following. Multiply x. So basically x to the power of n would be just x multiplied by x to the power of n minus 1. And since now n minus 1 is even, we can apply the formula for when n is even. And at that point we get x multiplied by x squared to the power of n minus 1 divided by 2, right? And so now that the final formula pretty much is just x to the power of n is equal to x multiplied by x squared to the power of n minus 1 divided by 2 if n is odd, and if n is even, it's just x squared to the power of n divided by 2. And if you want a base case, we can just put that x, we can put a base case, but it's not really useful. But the base case would be that if n is equal to 0, then we know that anything to the power of 0 is just 1. And you can also, if you want, add n equal to 1. In that case, x to the power of 1 is just x, right? And yeah, so pretty much that's what it is. So just to show how powerful this is in reducing the number of computation, let's take an example here. So for x to the power of 6, what do we have? So for x to the power of x, if we compute it using the usual method, we will do something like this, right? So we'll do six computations, right? Or 6 multiplications. Just call them multiplications. Now, if we use the method that we just described, then what we will do is x to the power of 6, x is even, so that's x to the power of 2 to n divided by 2, which is 3. Now 3 is even, so let's just take y equal to x squared, so we make this easier to write. And so this would mean here that x to the power of 6 is just y to the power cubed. So y to the power of 3, 3 is odd, so we apply the add formula, which is that it's equal to y multiplied by y squared to the power of n minus 1 divided by 2, n equals to 3, so n minus 1 is 2. So n minus 1 divided by 2 is just 2 divided by 2, which is 1, right? And so if we plug this into the formula, which is, if we plug this into x squared to the power of 3, right? And so y is x squared, so that would mean we have x to the power of 2 multiplied by x to the power of 2, the whole thing to the power of 2, right? We just plug in y in its position here, right? And so here what we need to do is just we compute, so what we will do is we compute this once, right? We compute x by x, so that's one multiplication, and then since we have the value here, we do one more computation to multiply, so we do one more computation to get, basically to get x squared multiplied by x squared here, right? And since we already know the value of x squared, we don't need to multiply again, and so we get here another multiplication, right? And then we multiply the two together and we get another multiplication. So you can see overall the number of multiplications that we would do here is just 3 multiplications. And so for just a number as small as 6, we go from 6 to 3 multiplications. And if the number is really big, it becomes bigger. But essentially you could see that since every time we are halving, almost, for the even case we do it like x multiplied by that, but pretty much it's just, if we kind of round a little bit, every time we are dividing by 2. And when every time you divide something by 2, that's just the overall time it will take to reach 1 is log base 2 of n, right? And so this pretty much would be the time complexity instead of the method where we are multiplying, which is O of n. And so this can reduce the algorithm to multiply from O of n to O of log n, right? Okay, so now let's see how can we write such an algorithm, right? So if let's use Python to write this. So the function would be, let's call it exponentiation of n, right? X to the power of n by squaring. So what would happen is first we would, there is one use case that I didn't mention, which is when n is smaller than 0. Let's say you have x to the power of minus 3. We can just convert this to the problem of n with n bigger than 0 by just doing 1 divided by x to the power of 3 and make this our new value y, and this ends up being just computing y to the power of 3, which fits this function, and we can just use that. And so let's apply that for n is less than 0. Then what we will have is we can just return, just to make this shorter to write, let's just make this exponent. So so it would be 1 divided by x, that's the new value for x, and for n it's just minus n, right? Now if n equal to 0, then we can do the base case that I mentioned earlier, which is just return 1, and if n equal to 1, we can do the base case of x, right? This is not really necessarily because it will fit with n is odd, but it doesn't hurt to put it here. And then we could do if n is even, which we can check by just checking modulo 2. So this is an even. At that point we can just return. So what is our case here is this one, so x squared to the power of n divided by 2. So x multiplied by x with n divided by 2. right? This I'm doing in Python just to get an integer. And then for when n is odd, which is the last else case here, then we could just return x multiplied by the same thing we are doing here, multiplied by exponent of x squared, which is x multiplied by x, and divided by 2. And so that's pretty much the algorithm to do here. But one thing you can notice with this function that we just wrote is that it's not tail recursive. So why is that, and why does that matter even? So basically what tail recursive is, a function, a recursive function like the one we have here, is tail recursive if the final result, which is returned here and here because of the if else and here, so if that function, so basically we can consider a function a tail recursive if the final result of the recursive call is the final result of the function itself. So if the result of the recursive call must be further processed, for example by adding 1 or by multiplying by some other number, or by let's say if it's a list adding an element in front or something, then it's not tail recursive. And so you can see, for example, in this case we are multiplying by x at the end here, and so that makes this function not tail recursive, right? If we were not multiplying by x but just returning the function itself like we are doing here, then that would be tail recursive. But why does it even matter, right? Why does it matter? Why do we care even if it's not tail recursive? So the problem is, if tail recursion is important because functions that are tail recursive can be implemented more efficiently than the general recursive functions that are not tail recursive by the compiler. And basically, for a function that is not tail recursive, what will happen is that we will need to push. So if you have the stack of functions, we have to push the return address of the function into a place in the stack, then jump to the called function, and so that we need to keep this reference so that we can, once we are done doing the operation, for example here we multiply with whatever value there, and we can return to that. And this basically means that for the recursive function we need to keep these addresses here, which would make use of the stack linear in terms of whatever number of recursive functions we will call. Basically it would make the stacks linear in the terms of the depth of the recursive function, right? And so when we have the tail recursion, though, we know the result as soon as we return from the recursive call, and so we don't need to store it in the stack. So we can skip the entire chain of recursive functions returning and just return straight to the original caller and not need to keep anything in the stack. And so it can be just a simple jump back to the caller, and so that means we will need O of 1 or pretty much O of 0 space in the stack. And so it makes basically when the function is tail recursive, then we can no extra stack space would be required, and so that's pretty good, right? So it improves the space complexity. And so how can we then do that for our function here to eliminate the O of log n space that we will need, right? So how can we do that? So a simple change that we can do here is that let's just use another function. So the way we are going to do that is, let's say we want to call exponentiation of n of x and so let's just call a helper and call it a helper for exponentiation and pass the final result that we need to return. Let's make it a parameter here and call it y, and have x and n. You will see why I'm doing this at the end. And then at the end I will just return, calling that helper with, it starts out as 1, right? The result we will multiply, and so to have something to start with, just like with addition we start with 0, we're going to start with 1, and we still have x and we still have n. And so what is the content of this helper function? So when n is less than 0, we will do the same thing we did previously here, which is just use this, and so would be just return a helper of we still have y and 1 divided by x and minus n, right? For the base case n equal to 0, we can just return a helper of same thing, y, x, and x equal to n equal to 0, we can just return the result that we stored in y, so that would be just return y. So it's essentially 1 multiplied by y, which is just y. And if n is equal to 1, then we need to return, before we were returning x and just letting the recursive call bubble up, right? Now the result of the recursive call, we are storing it in y, and so we can just return x multiplied by y. And so we can see here, why am I using this y variable? Because instead of multiplying here, I want to multiply in the parameter, so that my function would be recursive, tail recursive, and since y is the final result instead of the return of the function, then I could just multiply x as part of the result, the final result, which is the value y. And so here, after that, I can check if n is even, which is this is equal to 0. Then at that point, I can return the same thing I returned before, which is x multiplied by x and n divided by 2. And so y stays the same, because at the end we will already multiply whatever is at x by y, right? And so here x multiplied by x and n divided by 2. Now if it's odd, that's where the change would happen, because that was where the function was not tail recursive. Instead of multiplying by x, we'll just call the helper function right away, and y is the final result, and so we will multiply y by x, and then we'll pass the same thing we were passing before. So this would be n minus 1 divided by 2. And so you can see the way we transferred it is from using this. We made the parameter be, the result be one of the parameters, and now instead of multiplying the result here, we multiplied it inside the function, and we ended up with a tail recursive, because there is no other processing happening after calling the recursive function, right? The last call is always the recursive call. And so this makes the function recursive, tail recursive, and makes the space that we will need to use constant. Yeah, so that's it for this. Next we'll see an iterative version of this, of an implementation of this algorithm. So to make this function iterative, especially when the recursive function was still recursive, it's very easy to turn it into an iterative version just by unrolling the what the recursion does. And so let's look at that. So iterative version. So for our iterative version, let's first define the function, which just gets x and n. And what we have is if n is less than 0, so we need to just do this. But since we are not recursively calling the function, let's just change the values. And so x becomes what we were passing before, right? Which is 1 divided by x. And n, since we were passing before minus n becomes equal to minus n, and then we continue. And if x is not less than 0, we'll just skip this this block after the if call. And so if n equal to 0, at that point, say we just got the parameter 0, then no need to do anything, we could just return 1. Now we do the recursive calls until we hit the base case, which is n equal to 1. We are done. So to do that, we do while n bigger than 1. We keep doing what the recursive function did here until we reach n equal to 1, which is the base case. In that case, we need to return x multiplied by y. So let's just leave space for the while calls here that will replicate the recursion over there, and just at the end return the value of the base case when n reaches 1, which was x multiplied by y. The same value that we had here, right? And so now we need to check if n is even or odd. And so if n is even, what did we do before? So before we just changed x to be this, so this is the new x, right? And this became the new n, and this value is the result, right? And so that's the value y. And so I forgot to initialize that, because here you could see at the initialization step we initialized y to 1 by passing it here as a parameter. And so I would need to initialize y here. So let's just say y starts out as equal to 1. And if n modulo 2 is equal to 0, y stays the same, but x becomes x multiplied by x. That's the new x value. And n becomes n divided by 2. Right? That's all it changes, and then it goes to the next iteration, which would be equivalent to doing the recursive call again. For the odd case, what changes is that this is the new x, right? This is the new n, and this is the new y, right? And so let's do that in order. So y becomes x multiplied by y, and then x becomes x, the new x, and then n becomes the new n, which is n minus 1 divided by 2. And that's pretty much it for this iterative version. We just took the exact function, a recursive function, turned the base case here into the limit of the while loop, and when we are done we return the value of that, and then turned these helpers, which are just changing the parameters and iterating again. We did the same thing. And that's pretty much it. And so you can see here the time complexity is the same as the previous solution that we did. So it's O of log n, and the space complexity is, since here it's not recursive, it's iterative, and we are not storing anything extra except this value y, so it's O of 1. Okay, so that's it for this quick lecture about fast exponentiation. Thanks for watching, and see you next time.